Hello, I'm Mr. Plow. Are you tired of having your hands cut off by snow blowers and the inevitable heart attacks that come with shoveling snow?
Uh-huh.
Then call Klondike 53226. Call now and receive a free t-shirt. Call Mr. Plow. That's my name. That name again is Mr. Plow.
All right, everybody, welcome to the notes on Chapter 6, Section 8. So we've been working with radical functions and equations. We've been solving, simplifying, doing all this stuff. And so now we're going to graph. Graphing is something that we continue to work on. It's not easy because it's not Algebra 1 anymore. We don't just have a bunch of lines and things like that. We're graphing things that have curves and things that turn and things that, absolute values, all these different things. And so, we just have to keep working on them and keep practicing them, and we'll get better. So let's take a look here. A square root function is the inverse of a quadratic function, okay? It's the inverse, and then we're going to talk about a restricted domain, okay? A horizontal line can intersect the graph of f of x equals x squared. You see this right here. In 2 points where f of negative 2 equals f of 2. So, for example, we have this axis of symmetry, and we get this, and that same horizontal line gives us the same y value. Thus, a vertical line can intersect the graph. So what we have here is, we have a vertical line intersecting the inverse. This right here just means the inverse of this f of x, okay? So the inverse of it, so because a horizontal line is going to intersect this one at 2 spots, a vertical line is going to intersect this one at 2 spots, all right? We can restrict the domain of f so that the inverse of the restricted function is a function. You'll recall from Algebra 1 and earlier from this class that this graph right here is not a function because it fails the vertical line test. But sometimes what we do is we restrict the domain so that we do have a function, okay? So that this right here is a function and its inverse right here is also a function, all right? Sounds complicated a little bit. We'll talk more about it. Okay, so inverses of power functions, y equals x to the n, with domains restricted as needed, form parent functions that are y equals the nth root of x. So all we're saying is that instead of taking x to the n here, the inverse of that function is just taking whatever that n is and making that the index and taking the root, okay? In particular, right here, we have f of x equals the square root of x is the parent function for the family of square root functions. Remember that this family have the general form right here, which should look familiar. That's tough to see. It should look familiar because we've used this general form, those letters, a bunch of different times, and they're going to have similar effects. Okay, so some key concepts. We have the square root function right here, the radical function right here. If we wanted to reflect it in the x-axis, we would just put a negative outside, right there and right there. If we want to stretch or shrink, then we would put an A out front. This should all seem very familiar. And then a translation horizontally by H and vertically by K. Those should all seem very, very familiar. Okay. Same letters we've been using for absolute values and quadratics and everything else. So, translating a square root function vertically, what are the graphs of y equals the square root of x minus 2 and the y equals the square root of x plus 1? So y equals the square root of x is this graph right here. Okay, it's the original one, it's the parent function, it's where we started. Should make sense, by the way, because if we put, for example, just want to make a table and look at some of these, for the parent function, if we put 1 in for x, the square root of 1 is 1. If we put 4 in for x, well, the square root of 4 is 2. And if we keep going out here, if we put 9 in for x, then the square root of 9 is 3. Okay, so those are how we're getting those points. If we have minus 2, all we're doing is we are shifting that graph down. Okay, the minus 2 is going to shift it down 2 units, so this same function right here is now, well, not everybody, is now just down. Okay, we're moving it just down to right there. Whereas right here in the red graph, if we have a plus 1, that's going to shift it up 1 unit. The domains of both functions are the set of non-negative numbers, but their ranges differ. Okay, their ranges are different. What would the graphs of y equals the square root of x plus 2 and y equals the square root of x minus 3, what would those graphs look like? So on the graph paper that hopefully you have or you grabbed from the back of the room, let's go ahead and try and replicate these graphs right here, y equals x plus 2 and y equals the square root of x plus 2 and y equals the square root of x minus 3. Go ahead and pause the video and do that now. Go ahead and pause the video. Okay, you've unpaused. Hopefully you got similar to what I got. I went ahead and included the parent function. This is y equals the square root of x. And then what we have here is I have the blue function in blue, y equals the square root of x plus 2. It's just everything shifted up 2. And then this function in green, it's just everything shifted down 3. You'll notice that it looks like we're only graphing half of it. We sort of are because we want them to be functions right now. So if I were to graph the bottom half of this right here, this blue one for example, we would end up with a line down here, and then that's not a function because it fails the vertical line test. So we're not going to do that. We're just going to graph the the top half of it for right now. Okay? Let's take a look and get this out of our way. Over there. All right, so translating something horizontally. Translating something horizontally, we'll actually put whatever we're doing inside the radical. So for example, right here we have y equals the square root of x plus 4. So you'll notice the parent function again is this black dotted one going right here. And then when we have a plus, we shift it left. When we have a minus, we shift it right. These should seem very, very similar to things that we've been doing for a long time now. So, you know, it's just a shift. This one right here is going to be a shift to the right. This one right here is going to be a shift to the left. Go ahead and do those and pause the video and get answers to those, then we'll take a look. Go ahead and pause the video now. All right, you've unpaused. Hopefully you got the same thing I got. For x, square root of x minus 3, that's this blue one right here. Everything was shifted to the right 3. And for x plus y equals the square root of x plus 2, hopefully you got this green one where everything was shifted left 2. All right. Okay, so recall from 2-7. We haven't done that yet. We'll talk about that how we can make a shrink. We're going to do that. Sorry, 2-7 is a long time ago with quadratics. Okay, and how this right here out front can make something stretch or shrink. This works still. If the absolute value of a is greater than 1, it's a stretch. If the absolute value of a is less than 1, it's a shrink. Basically, same exact rules that we've been working with quadratics this whole time. Okay. We can also have negatives here. You'll notice in the example, the negative, that's just going to flip it upside down, and it's -1/2. So we're going to see the bottom half of it, like we have right here, and it's also, instead of going over 1, down 1, it's going over 1, down 1/2. And instead of going over 4, down 2, it's going over 4, down 1. So we take the coordinates, we multiply them by the 1/2, you know, the same. Again, making a table is always useful. Instead of 1, 1, we have 1, 1/2. Instead of 4, 2, we have 4, 1. Instead of, you know, 9, 3, we have 9 and 1.5. All those kind of things. Okay. So, and then what we have also is that, you know, we can have, this is going to shift it right 3, and this is going to shift it up 1. All these different things. Okay. Same stuff that we've been doing for a while now. This shouldn't be that difficult. Let's go ahead and take a second and try and get the graph to number 3. Y equals 3 times radical x plus 2 minus 4. Okay. And when in doubt, make a table. Go ahead and pause the video right now and try and solve that one. Graph that one. So I included my table here. I wanted to kind of show you my thought process. You know, some of you might be able to just go to the original, you know, graph the original, the parent function. You know, we have these 3, okay? And so we're going to shift it. We know we're going to shift it left 2 and down 4, so that's easy. So we come, you know, not everybody. We go ahead and come down here. So that takes this point, I'll do this in a different color. That moves this point to right there. Okay, so we go down, left 2 and down 4. Then instead of over 1 up 1, we're going to go over 1 up 3 because it stretches it. And then instead of over 4 up 2, we're going over 4 up 6 because of this 3 right here. So some of you may have looked at the parent function of that. If you couldn't, just, this is never a bad place to start with -2, -1, 0, 1, and 2. And I put those in for x and I solve. You'll notice right here I got an ugly number and I got an ugly number. I don't want to graph those. I'm looking for integral points, points that are integers. So I do all that. I get this blue function here, and that is the graph. Okay, not really complicated, but just you can go about it either way. You just need to have a way. That's the key. Get those out of the way. All right, so solving a radical equation by graphing. So we have this model right here for the population of Corpus Christi, Texas, between the years of 1970 and the years and 2005. And then they want to know, what year was the population? 250,000. So really, all we do is we graph this first one, okay, and then we graph the point. Or y equals 250,000, and you just find where they intersect. It's really not that complicated. You could also, put 250,000 in for the population right here, subtract it to the other side, graph that, and just find the root. Either way, you're going to get your answer as 1987. Okay? So now, using that same idea, and this is on your calculator, okay? So you got to know how to do this on your calculator. What year was the population of Corpus Christi? 275,000 people. Go ahead and pause the video and find out what year was the population 275,000. All right, you've unpaused. Hopefully for that one you got 1999. All right. This problem, you'll notice, used cube root. The function for a cube root is the inverse of a cube. So unlike y equals square root of x, the domain and range of f of x equals the cube root are all real numbers. Really simply, this can be a function because it always passes the vertical line test. So it's going to go forever left and right and forever up and down. So the domain and range are both all real numbers. All right, so graphing a cube root function. Let's take a look at that. First, we graph the parent function, so that's step 1. Then we apply, whatever this is going to multiply everything by 2. This is going to shift stuff left and down 4. So really that's all we're doing. We multiply multiply the y coordinates by 2. That gives you a vertical stretch, and then you take those same points and you shift them 1 unit to the left and 4 units down, and that's it. Okay. Very similar to everything that we have been doing. So let's take a look at this one. You'll notice, I'm going to help you out a little bit. Just a quick hint here. You'll notice that this -1/2, this looks different. Move the 3 over here. Rewrite this, okay? Rewrite this so that it makes sense to you. Rewrite this as y equals -1/2 times the cube root of x minus 2 plus 3. Same exact thing, but now it sets up into what we want it to look like. So go ahead and pause the video here, graph that. All right, you've unpaused. Hopefully your graph looks something like mine. You can see that I've shifted over 2 and up 3, so that part's right in there. That's easy. And then because of the negative right here, instead of my end behavior changed, instead of being down up, it's up down. And then everything, the y coordinates have been multiplied by 1/2. So instead of going over right here, instead of going over 1 up 1, I went over 1 up 1/2. Instead of going over 8 up 2, I went over 8 up 1. If that doesn't make any sense to you at all, that's fine. Make sure when you get to class, you've made a note of that somewhere, and we get your questions on that answered, okay? But make sure you have at least the right answer down, and then that'll give us some place to start from. All right. So we can graph functions of the form y equals the nth root of bx plus c using transformations if you can simplify the radicand so that the x has a coefficient of 1. Okay? So here's what we mean by that. How can you rewrite this so that x has a coefficient of 1? So what we do is we factor on the inside. So we factor right there, and then this is now, we can take the square root of this 9, so the 3 comes out. So it's been stretched by 3 and translated 2 to the left. Okay, so that's how we do that. We just have to factor. So here, for example, how can we write this? Y equals cube root of 8x plus 32 minus 2 so that we can graph it using transformations. What we would do is, and I'll walk you through this one because these I do think are a little bit more complicated. Hopefully you recognize that that has the greatest common factor of 8. And so what happens is we're going to factor the inside. We're going to make it look like this. Y equals the cube root of 8 and then x plus 4. Okay, and then we still have this minus 2 outside. We can take the cube root of 8, which is 2. And then all that's left inside is x plus 4. And then from there, we should be able to do it. It says describe the graph. That graph has been translated 4 units left and 2 units down. And then it's, of course, it's also been stretched by that 2. Okay. Describe the graph of y equals the absolute value of 9x plus 18 by rewriting it in the form of y equals a times x minus h. And how is this similar to what we did in problem 6? So if we were to rewrite that, that part's probably pretty easy. Let's get this out of the way. We would rewrite this right here by just doing y equals 9 times the absolute value of x plus 2. Okay, because we factored. That is the graph of 9 times the absolute value of x, and then it's been translated 2 to the left. All we're doing is rewriting the function so it has an absolute value of 1. That's it. So it has a leading coefficient of 1. That's it. Not too complicated. Hopefully not that much trouble. And that's it. That's it for the notes. Hopefully that wasn't too bad. I will see you next time.